Moving on to the next topic, hunting in synchronous motor. So I remember discussing this topic in induction motor as well. So what is this hunting? Hunting is a process or the phenomenon where your rotor is subjected to vibration due to the sudden change in load. So whenever the load keeps changing, the shaft is coupled to the load, and in turn, this side within the motor, the shaft and rotor are coupled. So the moment you change the load applied to the motor, the immediate effect will be on the rotor of that machine. So the rotor takes some time to settle with that new load or the change in load. So in meantime, it will be subjected to oscillation. So that condition where rotor is subjected to vibrations or oscillation due to the sudden change in the load is what is referred to as hunting. So in case of synchronous motor, how it happens, because it is happening, what is the problem and how to overcome that or suppress that, we will see now. So in synchronous motor, because your synchronous motor is rotating at synchronous speed, rotor pole and stator pole axis will both be coinciding. That is, they are running in the same speed. So both pole axis, that is stator pole axis and rotor pole axis, will coincide with each other. Now, when the load which is connected to the motor suddenly changes by a large amount, this sudden change or sudden large change by the load cannot be handled by the rotor. So this change in the load affects the rotor pole axis to fall back with respect to the stator. So now the rotor tries to slow down, or it tries to catch up that new value. So it will not be able to judge exactly what is the change in the current for a small duration of time, or change in load for that small duration of time. So what happens is it will be trying to slow down at one case. So in order to pick up its speed or to coincide with the stator axis, it will produce the torque which is much more higher than what is demanded. So because of which it will go beyond the new position or the new load position what is there now. So at this time, the rotor will try to reduce the load angle, and again it will swing back. So this keeps on happening. So it will not be able to exactly decide what is that new load present on the motor at that instant of time. So for that sudden load, it will decrease. Again, to cope up, it will increase, again decrease, again increase. So this increase, decrease, it will be swinging between the or across the new value of the load. So this periodic swinging of rotor on both sides of the new equilibrium position is only what is called as hunting. So such oscillation is nothing but periodic swinging of this rotor on both sides of the new equilibrium position. So the rotor oscillating about its new equilibrium position due to the sudden application or removal. Change in load can be either addition or removal. So by sudden addition or removal of the load is what is referred to as swinging or hunting in synchronous machines or synchronous motors. So because of this hunting, the load angle delta changes its value about its final value. So how is it changing now? Now you can observe here, we have considered again the phasor diagram. So you have the supply voltage here. Current IA is the new value what we require now. And the corresponding resultant EMF will be ER. But before it settles down at this IA or ER, it will be swinging on both the sides. So the value corresponding to IA, we will take it as ER1, and the value corresponding to IA2, we will take it as ER2. But here we are not changing the excitation. Both cannot be done at the same time. So we are keeping excitation same, because of which your back EMF remains same. So back EMF is supposed to remain same, EB itself. But you can see here delta, this angle, one line which is there in between is also your back EMF line. And the angle between that back EMF and this voltage, we take it as load angle delta. Now this delta is what is the new value, what we want, or change in the load angle, what we are expecting. But before it settles down at this value, we will get delta 1 and delta 2, one which is lesser than delta, other one which is greater than delta. This is because of that hunting phenomenon or that oscillation of the rotor on both sides of its equilibrium value. So this is due to this, what happens for same excitation, you can see the current drawn by the motor keeps changing. So because there's a sudden change in the load, this affects in turn by drawing the more current from the supply. So this may cause problem to the other appliances which are connected to the same line. So it is not only affecting the motor, it is also affecting the other loads which are connected to the same supply. So in case if such oscillations continue for a longer period of time, then there are chances that this motor can fall out of synchronism. That is, the rotor fails to, once it falls out of synchronism, then it will no more be rotating as synchronous motor. So whenever there is a sudden change in load, a motor will be subjected to very high mechanical stress. That is, your oscillation is referred to as mechanical stress, and this in turn leads to the drawing of more current from the supply. And this more sudden draw of more current will lead to electrical stress, because more current means you have more losses, more heating, which again leads to thermal stresses. So there are various stresses which is present in the motor. So because of this hunting, that is, whenever there is a sudden change in the load on the rotor takes time to settle down on this new position. So this leads to oscillation, which is referred to as hunting. And this oscillations causes the mechanical stress and the electrical stress on the motor. So a certain care has to be taken care in order to uh, keep this oscillations or suppress. Of course, we cannot completely vanish this effect. Once the motor is there, once there is a change in the load, the effect is definitely there. But the result of this change should, we have to suppress, because it is not that favorable. So we have to suppress. How do we suppress that? By using damper winding. We already know, we are already familiar with this damper windings. These damper windings are kept in the rotor, and these are basically used during starting. So we will start this motor as induction motor basically. So this additional winding which is placed in the rotor slots and they are short circuited are called as damper winding. So this is the same damper winding which we have discussed already during the starting methods. So what happens because of this damper winding is, whenever there is a sudden change in the load, we know that the rotor starts to oscillate. So that process is what is called this untangle. There is now the motion between the damper winding and the rotating magnetic field. Before, that is, once we start as induction motor and then we coincide the rotor pole axis and the stator pole axis, they'll be running at synchronous speed. So there, the relative motion between the damper winding and the rotating magnetic field will be zero. There is no effect of this, or there is no significance of the presence of this damper winding once the machine is running as a synchronous motor. But now, because of sudden change in the load, the rotor will pole axis will be now swinging around its new value. So when this is happening, there is a small relative motion between the damper winding and the rotating magnetic field. So once the relative motion is there, EMF gets induced. Now, according to Lenz's law, the direction of this induced EMF will oppose its own cause. So why is this EMF getting induced? Because of the relative motion. So why is that relative motion getting created? That is because of the sudden change in the load, that ultimately that is your hunting phenomenon. So this damper winding will now oppose its cause. That is, this oscillation itself is its cause. So damper winding tries to damp. Damp is nothing but suppress. So it tries to suppress the oscillations, and it will make it or it will help rotor to stabilize on its new equilibrium position as quick as possible. So by this, the damper winding is helping to suppress or minimize this hunting effect minimum, to the minimum value. So the time taken by the rotor to settle at its final equilibrium position after hunting is what is referred to as settling time, setting time. Now you can see here I have drawn two oscillating curves here. One is taking a longer time to settle down to its new equilibrium position. So that time is much longer, and that is without using this damper winding. Now once damper winding is used, you can see there is a second curve here which settles down at its new equilibrium position very quicker. So the time taken when the damper winding is present to settle down by the rotor because of hunting is much lesser than that when the damper winding is not present. So this is important. So they can ask you to discuss the use of damper winding to prevent hunting. So in that case, you have to discuss what is this hunting, why it is present in the machine, and you have to give this phasor diagram, and then you have to discuss how this damper winding is actually suppressing the action of this hunting, and you have to give this graph in order to show how this damper winding is suppressing the effect of hunting. So this topic is important. Next one is synchronous condensers. This can be asked as application of synchronous motors. So this is one of the most famous, or the pretty oftenly used application of synchronous motors. So basically synchronous motors are used as synchronous condensers. So what are it? We will see now. Now, whenever synchronous motor is on no load and it is over excited condition, then we have seen that the power factor angle will be leading in nature. Now, if this load angle is made very small, then the power factor angle will be almost 90 degrees. So almost it is leading by what angle? It is leading by 90 degrees. So when it is leading by 90 degree, what do we say is we call it as zero power factor because cos 90 is zero. But what is the power factor position? It is leading. So we call it as leading power factor condition. So when the synchronous motor is over excited and it is at no load, and this load angle is very small, the power factor angle will be 90 degrees and the power factor condition is referred to as zero leading power factor condition. Now this zero leading power factor exists only in case of capacitors. So this characteristics of zero leading power factor is similar to the normal capacitor. So when we take capacitor, we know that it is always the angle between the voltage and current will be leading. Current will be leading voltage by exactly 90 degrees. So that is what is referred to as zero leading power factor. So whenever the synchronous motors are over excited under no load condition, it more or less behaves like a capacitor. So that behavior or that condition where this overexcited synchronous motor under no load condition is operated as or behaving like a capacitor is what is called as synchronous condensers or synchronous capacitor. So why now we know that this synchronous motor can be made to behave like synchronous condenser. But what is the use we will see? The synchronous motors are basically now this is behaving like a capacitor. So they are very well known for supplying the reactive power, that is to improve the power factor. So the synchronous condensers are very well used as the devices to improve the power factor. Now, what is this power factor improvement? We will discuss or we will see first. Now, when we say power factor, we know the value can vary from 0 to 1. So in this range, there is a certain range where which we call it as optimum value. So it is very important. If not the domestic loads, commercial loads and industrial loads have to always operate their loads by keeping this power factor into consideration. So they have to maintain the value of power factor within the optimal value in order to improve the overall efficiency, not only of their system, also the supply system, the utility system. So in case if the power factor goes low, what happens? We will see now. What are the disadvantages of the lower power factor? We know that power P is given by VI cos phi. So now in turn the current is given by power by V into cos phi. Now we are not touching the supply voltage. So in order to maintain constant power here, if the power factor decreases then the current will increase. So if we say there is a low power factor, that means in turn the current drawn by the supply should increase in order to maintain same power to the load. So the in turn effect of this low power factor is the current is much higher. So this high current due to low power factor will cause following disadvantages. What are they is, now once the current increases, the size of the conductor should be more in order to handle that increase in current. So because of which the cost of the system will increase. You have to invest more on the conductor. That is one disadvantage. Then the power factor is given by the ratio of active power to that of apparent power. So the active power should remain constant. So in order to keep this active power constant, if the power factor decreases, then you have to increase this kVA supply. That is, the demand of this kVA increases. So if it has to supply more kVA, then the rating of alternator and transformer should be more. So this again leads to the increase in the cost. Again, where are these alternators and transformers? They are in our generation, they are in transmission, they are in distribution. So all ratings has to be increased, which increases the cost. And then the large current means we have more copper loss, because of which there is more heat dissipation and the overall efficiency of the system is lesser. And because there's a sudden draw of a large current from the supply, this causes a drop in voltage. So these voltage drops in transmission lines, alternators, the other equipments in the transmission and distribution will lead to poor regulation. So we again, to keep up this regulation value, we have to use some other method in order to compensate this drop. An additional equipment has to be used, which again increases the cost of the system. So that is why this is the reason why the power factor has to be kept at the optimal range. So it is very, very important to maintain the power factor at a reasonable value, so that in turn the current drawn by the motor will not be much higher. It will be only to restricted to that value for which the machines are designed. So how the synchronous motor is helping us to improve the power factor, we will see now. So we already discussed the low power factor increases the cost of the generation, distribution, and transmission of the electrical energy. So it becomes very critical for us to correct this power factor whenever it goes below a certain optimum range. So this can be done by using synchronous motor across the supply to which the other loads are there. And we have to operate the synchronous motor under no load condition and with overexcitation. Now let us say V is the supply voltage. We are all to plot the phasor diagram, we only take per phase values. So V phase is the applied voltage. Let us say I1 is the current drawn by some other load which is operating at low power factor now. Then the phi1 is the angle between this current I1 and supply voltage V. Now this angle is very high, because of which the power factor is low. When I say cos phi is low, that means the angle is higher. So now if we connect the synchronous motor, now it is under no load and it is over excited, it behaves like a synchronous condenser. That means basically it is behaving like a capacitor. So it tries to draw a leading current with a large power factor angle. So now this I2 is the current which is drawn by the over-excited synchronous motor, that is nothing but the synchronous condenser. So there are two components of current which is drawn by the supply. One is the current drawn by the actual load which is present there at low power factor, that is I1. Other one is the current drawn by the synchronous condenser at leading power factor, that is I2. Phi1 and Phi2 being the power factor angle of the load and synchronous condenser respectively. Now, if we take the phasor sum, we get the supply current, and that supply current we will call it as total current now, that is IT. Now, if I take this angle between this supply current and the voltage, you can see the angle is lesser. Smaller the angle, power factor angle, more will be the value of cos phi, that is power factor. So this is how by using making synchronous motor to run a synchronous condenser, we can improve the power factor of the load. So thus by using synchronous motor as synchronous condenser, the power factor of the combined load. Why combined load is because this motor itself is a load now, but we are not using motor alone. There we have one more load there which is having a very low or the poor power factor. So in order to improve this power factor, we are using this synchronous motor under no load condition and under over excited condition, which makes synchronous motor to operate as synchronous condenser. And by using this, that is by operating synchronous condenser together with the other load, is what is referred to as combined load. So thus by using synchronous motor as synchronous condenser, we are improving the power factor of the combined load. And this is how we can, this is the important application of synchronous motor.